Hi, this is Mrs. Myers, and today we're going to learn 7.3, Proving Triangles Similar. It's a two-day lesson. I'm going to put it all in one video, but you can fast forward to day 2 if you already have watched day 1. Okay, so we're going to actually be learning 3 new postulates and theorems that are going to relate to similar triangles. Now we've talked about similar polygons. This is all just triangles. So just as a reminder, 2 polygons are similar if their corresponding angles are, hopefully you remember, corresponding angles are congruent and corresponding sides are proportional. So they're in the same ratio as each other. So for these similar triangles then, if you remember, angle A is going to be congruent to angle, well, let's look here. A corresponds with V in our similarity statement. So angle B is congruent to T because it corresponds to angle T. And angle C is going to be congruent to angle W. The sides then are in the proportion AB is to VT, and what relates to TW, that was the last of the first, so BC. And then, so we have AB, BC, we just need AC. AC relates to VW. Okay, that's just a reminder. So, in order to tell if 2 triangles are similar, now I'd like you to think back for a minute about when we did triangle congruence, right? 2 triangles could be congruent to each other if, let's say, we knew this side was congruent to that side, this side was congruent to that side, and this angle was congruent to this angle. If you remember, that would have been side, angle, side, congruence postulate. We said with congruent triangles, all 6 parts are congruent, right? 3 sides are congruent to 3 sides. 3 angles are congruent to 3 angles. But instead of needing to prove all 6 parts, we really just needed 3 of them, side, angle, side. And then, of course, we learned side, side, side. This is congruence, right? We learned angle, side, angle, etc. A, S, and HL. Those were the ones that we learned. With similarity, it's actually very similar. No pun intended. We're going to learn postulates and theorems that do the same thing as those congruence postulates did for congruent triangles. Here we're talking about similar triangles instead of congruent triangles. So what we have to do is use one of these postulates. The first one is AA, similarity. Now, we could call it AAA, but what do we know in a triangle? If we know this angle is congruent to this angle, and the second angle is congruent to the second angle, then we had that third angles theorem, if you remember, that said, well, if you know 2 pairs of angles are congruent, the third one has to be congruent. So we really don't even have to mention that third one. So it turns out that to prove 2 triangles similar, now this does not work for all shapes, this only works for triangles, if they have 2 pairs of congruent angles, then they are similar. So S is congruent to M, if we could show that, and R is congruent to L. That's enough to say, well, then these have to be similar. So with triangles, if the angles are congruent, then the sides will automatically be proportional. So if we look at these examples here, are the 2 triangles similar? So presumably we're going to be using AA here. Well, they only give us 1 angle and 1 angle. But we know from previous knowledge that this Don't show this message again. Okay. That this angle has to be congruent to this angle because of vertical angles theorem. Remember that? Okay, so now we have two pairs of angles congruent, green to green and red to red. So, are they similar? Yes, by AA. And vertical angles theorem. Number 2, we have this is 30 degrees. This one is 70 degrees. We don't know this one. This one right here. They haven't told us what that angle is. Could we figure out what that angle is? Sure. The three angles of a triangle add up to 180. So 30 plus 70 is 100. That means angle K must be 80 degrees. Well, let's look at the other polygon then. One is 70, so that matches. Let's make it red, double red. That matches our double red over here. But we have an 85-degree angle there and only an 80-degree angle here. So, not similar because only one angle is congruent. Only one pair of angles are congruent, and we need two pairs. Okay, number 3. We know this is a right angle, so that's 90. We know this is a right angle, so that's 90. This is 39. In order to get this third angle, we're just going to do 39 plus 90, take it away from 180, and we're going to get 51 degrees. Now we look at the other triangle. We have a 90 degree and a 51 degree angle. That makes the third one has to be 39. So yes, they're similar. And what we used here was the triangle sum theorem, right? They add up to 180, and that's how we found that two pairs of angles are congruent. Okay. So that's the AA similarity postulate. There are two other postulates to use to prove triangles are similar. Oh, for a second I thought it wasn't recording. Here we go. Okay, sorry about that. 7.1 theorem says SAS, side angle side similarity. So it turns out that if we have two sides with information and one angle on each triangle with information, then we could show that triangles are similar. But we have to be careful, because anytime we're involving sides, we're talking about not sides being congruent now, but sides being proportional. So we can know that two angles are congruent because with similar triangles, angles are congruent. So that's a pair of angles congruent. But what we have to know about the sides is that they can form this true proportion here. They are proportional sides. It has to be a true proportion. If two pairs of sides are proportional and their included angles are congruent, then the triangles are similar. So that's SAS, and we'll see an example of that in a minute. The next one here is SSS. So this theorem is just knowing that all the sides are proportional to each other. No angles involved, but we can check the sides being proportional on two triangles. So down here, are the triangles similar? Well, here it looks like we are not dealing with any angles. They didn't give us any angles. So that eliminates the possibility of AA or SAS similarity. Here, we're going to use SSS similarity. Notice when we write SSS, we're going to put that little similar symbol after it, because if you remember, there was an SSS congruence theorem. We don't want to get them confused. So with SSS similarity, we're going to put the little similarity symbol after it. Okay, so are they similar? Well, we have to check all the pairs of sides. Let's write a ratio of the smallest side to the smallest side. So the smallest side here is 6. The smallest side on this one is 9. So I'm going to use the ratio 6 to 9. If I'm going to do the medium side to the medium side, it's going to be a ratio of 8 to 12. And if I do the longest side to the longest side, it's going to be a ratio of 10 to 15. Now, remember we said there's two ways of checking if things are similar using sides. We could simplify each of these ratios. 6 over 9 simplifies to 2/3. Divide top and bottom by 3. 8 over 12 simplifies to 2/3 because we divide top and bottom by 4. 10 over 15 simplifies to 2 over 3 because we divide top and bottom by 5. So since they all have the same ratio, that means that they are similar. Ratios are the same. So that means all the sides are proportional, so they're similar. Now remember, there's another way to do it. But either way, we have to check all 3 pairs of sides. So we could set up proportions. We could do 6 is to 9 as 8 is to 12 and check this. Cross multiply and we get 72 equals 72 and that checks out. Then we could do, excuse me, 8 is to 12 as 10 is to 15, and we could cross multiply again and get 120 equals 120, and that checks out. Then we could do the third one. So we did blue to green, we did green to red, now we need to do blue to red. So 6 is to 9 as 10 is to 15, cross multiply, and you get 90 equals 90, and that checks out. So all 3 check out to be proportional. Therefore, yes, this is similar by the SSS. Yes, by SSS. And the similarity statement then would be, now you got to be careful of your order. Let's say STU is similar to, now what corresponds with S? S is between the red and the blue, so between red and blue would be X. If you don't want to think of red and blue, you think of between the longest and the shortest side, between the longest and the shortest side. Okay, so S goes with X, and then T goes with between blue and green, so V. So XVW is going to be my corresponding order. Oops, triangle, XVW. Okay. So the 3 ways of proving triangles similar are AA similarity, SAS similarity, or SS similarity, SSS similarity. Okay, so there's some examples here on checking if the triangles are similar. Here we have overlapping triangles, and there's some tricks here now. This triangle, my blue triangle, and the red triangle are overlapping. So they actually have an angle in common. They share this angle. So that's one pair of angles that's congruent by reflexive. Angle K congruent to angle K by reflexive property. It's the same exact angle. So maybe we can use SAS here. We have an angle, and it looks like we have relationships of sides. Now, there is a trick here. If we draw these triangles separately, this side is 8, this side is 12. What's this side? It's not 2. You got to be careful because this side is going to be the whole thing 8 plus 2. So that's going to be 10. And then the same thing on the bottom. We've got 12 on the blue, but then we have to add the 3 to get the whole side is 15. Be careful of that. You want to not just use 8 and 2 and 12 and 3. That doesn't make sense. 8 is the side of the blue triangle. 10 is the whole side of the red triangle. So now we have to check if these are in the same proportion. So 8 is to 10, and 12 is to 15. You can cross multiply. You get 120 equals 120. And they are similar. Remember, the other way to do it is 8 is to 10, simplifies to 4/5, and 12 is to 15, also simplifies to 4/5. Same. Okay, so they are similar by SAS. And the similarity statement would be triangle KLM is similar to triangle, sorry, not KLM, KLP, similar to triangle KMN. Make sure you have corresponding parts. So that's a little trick when they're overlapping. You can use that overlapping part, in this case angle, as being congruent to each other. Another really common use of similar triangles would be a diagram like this one, where you have a segment drawn parallel to one of the sides. Remember, when we have parallel lines, we can look for congruent angles, because parallel lines have alternate interior angles congruent, corresponding angles congruent, alternate exterior angles congruent. So all of those things can be indications of congruent angles if we have parallel lines. So in this case, this is actually a proof. We are given that these lines are parallel. We want to prove that the triangles are similar. So what information do we have? Number one statement here just states the given. The lines are parallel. Look at number 2. It says angle A is congruent to angle CDE. We need a reason for that. Well, if these two lines are parallel, what kind of angles are these two angles? Hopefully you remember these are called corresponding angles, so it would be the corresponding angles theorem that says that they're congruent. Then it says angle B is congruent to angle DCE. B is congruent to DCE. Again, corresponding angles theorem. Now, oh, they forgot a step here. We got to add a step in here. Oh, no, we don't. We actually don't, because we don't need all three angles. We could use all three angles because angle E is congruent to itself by the reflexive property, but we actually don't need it because remember, with the similarity postulate, it's just called AA similarity. So as long as you have two angles that are congruent, we can say triangle ABE, that's the big one, is similar to triangle DCE, which is this smaller one. They're similar because they have two pairs of angles congruent. So we would call this AAA similarity. In a proof, anytime you're using a statement as two triangles similar, your reason is going to be either AA similarity, SAS similarity, or SSS similarity. Okay, I want to show you one other problem that is really common, and that is like number 1, and you'll see it again in the proof down here. It kind of looks like a bow tie. I call it the bow tie problems here. Let's do the proof. The bow tie problem here says this is parallel to this. So we are given that the lines are parallel. Looks like my given got cut off here, but lines are parallel, which lets us say that angle QMN, that's this one, is congruent to OPN. Well, these lines are parallel. Look at the Z, right? Those angles form a Z. What kind of angles are those? Alternate interior angles theorem. Alternate interior angles theorem. So if you know those lines are parallel, those two angles are congruent by alternate interior. It gives alternate interior angles theorem again as another reason. We need another pair of angles. That's going to be angle O is congruent to angle Q by alternate interior angles theorem as well. Now, the two triangles are similar then by AA similarity. Okay, so keep that in mind for number 1 as well. There's parallel lines. Okay, I'm going to move into day 2 now, right at the 21-minute mark. So proving triangles similar using indirect measurement. So this is going to be day 2. If you're watching this for the first time, you can, just finish with day 1, and now hopefully you've fast forwarded to day 2 if you are on the second day of this lesson. Okay, so there's 2 methods that are really going to be the most common that we use for indirect measurement. The first one is the shadow method, where if you're outside and it's a sunny day and there's shadows on the ground, you can find the heights of certain objects just by knowing the ratios of the shadows. So, for example, if you hold a yardstick up, which is 3 feet tall, and you measure its shadow is 6 feet, then when you go to a really tall object like a tree where you don't have a tape measure that can measure all the way up the tree, you could just go along the ground and measure the tree's shadow. If you do that, you've created 2 similar triangles. Now we just need a proportion to solve for the height of the tree. So if you really want to know the height of a tree, you can measure its shadow, compare it to a shadow of something you know the height of, and you can set up a proportion. This proportion would be 3:6, as x is to 24, and we would solve. You guys know how to solve those proportions. The second one is overlapping triangles. This triangle and this triangle, still shadows, but you're just setting yourself up in the wake of the other shadow. You're lining up your shadow on the ground so that it ends exactly where the shadow of this flagpole ends. So you're just lining up your shadows so they end in the same point. If you do it that way, you have overlapping triangles, but they're still similar overlapping triangles. Oops. So here we have the height of the flagpole, and here we have our height is 5 feet. Oops, 5 feet 4 inches. Then we have my shadow is 12 feet. And the shadow of the flagpole, look at this, you got to make sure it's the whole thing. 12 plus 27, which is 39 feet. Okay, for this one, 5 feet 4 inches really gives us an indication that we're going to have to put everything either into feet or everything into inches and get everything in the same unit here. 5 feet 4 inches is 64 inches. 12 feet is 144 inches. And so we have our height here, and 39 feet is 39 times 12, which is 468 inches. So now we have everything. We can write a proportion. 64 is to 144 as h is to 468. Okay, you're going to try this one on your own. I'm actually running out of time. The bell's about to ring. So I want to get to this mirror method. The mirror method is kind of cool because you can actually do this with your house or whatever, if you want to know how tall your house is. You step away from your house and you place a mirror on the ground and you back away from the mirror. So you're going to walk backwards here, looking with your eyes into the mirror. And you're going to stop right when you can see the top of your house reflecting right in the middle of your mirror. Wherever you stop, you're going to mark your spot right there. Because the measurements that you need here are the distance from the bottom of your house, in this case from this cliff, to the middle of the mirror, which says 34 feet, and the middle of the mirror to where you stopped. You stop when you see the tip of your top of your house in the middle of the mirror. So that's where you stopped. That was 6 feet from here. Then if you know your height, this person's height is 5.5 feet. Oops, there's spell. You could find the height of the cliff using these similar triangles. So we're going to do height of me is to the height of the cliff as this distance from me is this distance from the cliff. Remember, all of these proportions could be written in different forms. I could have done height of me to distance from the mirror, me from the mirror, and then height of cliff to distance of cliff from the mirror. Either way, remember, you are going to get the same cross products. Okay, so we will talk about this more in class, and thank you. I'll see you soon.